Okay. Is a visiting graduate student at Biomedical Imaging Research Institute at Cedar Sinai Medical Center and a PhD candidate in the University of California, Los Angeles. His research mainly focuses on developing novel AI techniques for medical image analysis. He is currently working on developing federated learning frameworks to perform end-to-end pancreatic cancer prediction. Prior to his current project, he has been working on various AI-related projects such as multi-vendor retinal image registration and medical imaging captioning during his master's degree at Duke University. He's going to speak about FedRNN, federated learning with RNN-based aggregation on pancreas segmentation.
Let me quickly share my screen. Can everybody hear me?
Yes, we can hear.
Okay. All right, let's get started. My name is Zengtian Deng, and today I'm going to talk about FedRNN, which is a federated learning algorithm that utilizes recurrent neural network as the aggregation method to perform pancreas segmentation on heterogeneous dataset. Okay, to get started, let me briefly introduce federated learning. Federated learning is a training technique that allows models to be trained on decentralized data, where the data is split in several locations and cannot be shared with each other. Currently, most of the deep learning models are trained in a centralized setting, where all data is gathered at a single site. However, for a multi-center study, the centralization of the data not only has privacy issues, but also has large cost on data transfer. And this is where federated learning can shine. The figure shown in this slide is a common type of federated learning called centralized federated learning, where within this method, there are clients training models with their local datasets, and there is a server collecting local models and aggregating them into a global model for all clients. One thing worth mentioning is that the server does not need access to any of the client's data. What it needs is only the trained model encrypted with privacy protocol. Now, within the structure of federated learning, the aggregation process at the server is an important process because it makes the final decision on what the global model will be. In the first paper of federated learning, Google proposed a straightforward aggregation method called federated averaging. In federated averaging, the server will perform a weighted sum over the gathered local models, and the weight for each local model depends on the data size of each local client. However, when the dataset at each local client is heterogeneous to each other, federated averaging may not be the best choice for optimization. For example, let's say we have a digit classification task and two MNIST datasets of the same size. As shown in the slide, one of the dataset only has the number from 0 to 1, and the other dataset has the number from 0 to 9. For federated averaging, the local models from the two datasets will always be the same. However, this is inappropriate since the second dataset with all digits has more features to be learned and therefore deserves more attention. Last year, to cope with the heterogeneity issues in federated learning, a method called dynamic weight averaging has been applied to federated learning by Shen et al. Different from federated averaging, dynamic weight averaging adaptively updates the aggregation weight based on how well each local model improves their training performance in terms of decreasing training loss. And it is shown to have improvement on the performance of pancreatic segmentation. However, since dynamic weight averaging only calculates the loss improvement from the previous round, it may not make full use of the longer history of the loss behavior. Additionally, as you can see on the right, since dynamic weight averaging only looks at one time point, the fluctuations in the training loss can also cause fluctuations in the aggregation weight, which may further impede the optimization process. Therefore, to better solve the heterogeneity issues, we summarize the purpose of our work as following. First, we develop a new aggregation algorithm called FedRNN, which utilizes recurrent neural network to take in the history of not only loss values, but also its corresponding aggregation weights to predict the optimal weight distribution. Second, we demonstrated that our method is able to yield better results than the existing federated learning methods in pancreatic segmentation. Third, we also compare our results with not only the centralized learning trained with one client's data, but also the centralized learning trained with the data from all clients. And such comparison to all dataset centralized learning has not been done in the previous literature. First, let me introduce the datasets. We use 3 publicly available datasets of abdominal CT scans, and all 3 of them have varied quality and number of cases. As for pre-processing, all scans are resampled by bilinear interpolation and then processed with Hounsfield unit windowing and intensity normalization. Random intensity shift and random affine transform were applied for data augmentation. The figures in the slide are example slices from 2 datasets after pre-processing. And as you can see that even after pre-processing, the 2 slices are still slightly different from each other. After the dataset, let's look deeper into the federated learning framework. For each training round, the global model is created at the server, either initialized randomly for the first round or aggregated by local models for the following round. The global model is then distributed to each client site for training. But before training, the global model is first evaluated at each client's dataset for cross-site validation. And then the models are trained with local datasets, encrypted by privacy protocol, and then uploaded back to the server for aggregation. The aggregated model will then be the new global model for the next training round. As for the privacy protocol, we adopted percentile privacy, which only keeps the model updates that are within the largest 25 percentile in terms of absolute value. Also, the aggregation model and the base segmentation model is jointly trained in our setup. Now, let's talk about detail of the aggregation process. For the aggregation model, we used element RNN, where the hidden state H-tau stores the information of the input history and is determined by the current round input X-tau and the previous round hidden state H-tau -1. For our methods, we sum the current round site-wise segmentation loss and the previous round site-wise aggregation weight as the input X-tau to the RNN model. For each aggregation weight prediction, we sequentially fed 15 pairs of previous aggregation weight and model loss to the RNN model, and only the output from the last pair will be used. Also, to ensure that the aggregation weight was summed to 1, we applied a softmax function to the output of the RNN model. We now know how RNN works for generating the aggregation weight, but how can we train it if we don't know what is the ground truth aggregation weight for each round? Well, to get around with this, we multiply the aggregation weight with the current round segmentation loss. The motivation behind this is that the overall goal of the RNN model is also to minimize the segmentation loss. So it can be included for the optimization as well. However, since there are so many layers and calculations in between, we can instead directly connect the predicted aggregation weight and the segmentation loss through a skip connection-like multiplication. And because the ideal value of the segmentation loss is 0, we can simplify the loss function to the second equation in this slide, which is to just minimize the multiplication of RNN output and the segmentation loss. In addition, to penalize the imbalanced performance across different sites, we adopted mean square error loss to penalize unbalanced behavior during the training process. Now, let's look at our results. Based on the dissimilarity coefficient, our method has shown better results on both site-wise and overall segmentation performance. Based on pair samples t-test, our method's result is statistically better than that of dynamic weight averaging. And we also have statistically the same result with all datasets centralized learning. However, you may notice that based on the case-wise average, all dataset centralized learning behaves even worse than dynamic weight averaging. And that is because the case-wise average die score is biased by the large number of MSD test cases. And it's most likely that although centralized learning performs better than dynamic weight averaging in other datasets, a few outliers in MSD dataset pulls down the average performance of centralized learning a lot. In addition, the figure on the right of this slide shows the comparison of segmentation results over the 3 federated learning methods. And as you can see that both federated averaging and dynamic weight averaging tend to overpredict the pancreas volume, as shown by the large red region, while FedRNN has a more precise prediction on the boundary of pancreas. For here, I want to show the aggregation weight and the training loss of FedRNN and dynamic weight averaging throughout the training process. In figure A, although FedRNN also has fluctuations on the aggregation weight over time, it preserves a major trend in the overall process. On the contrary, with dynamic weight averaging in figure B, the aggregation weight fluctuates a lot and is getting worse and worse over time. From figure C, it is difficult to tell the difference between the loss of 2 methods, but since FedRNN looks back 15 rounds during the training process, we also plotted the training loss in 15-round running average as shown in figure D. Now you can see that the loss of FedRNN, which is the blue line, drops faster than the dynamic weight averaging loss, and overall, it is able to reach lower training loss than the dynamic weight averaging, which shows that by having a smoother transition in aggregation weight, FedRNN is able to further optimize the model instead of getting stuck around the local minimum. To summarize, the major discovery we found in our experiment is that a history of training loss and aggregation weight can be helpful in optimizing the federated learning model when dealing with heterogeneous data. And to validate it, we introduced FedRNN, which showed better performance than the existing federated learning models, and also showed possibility to reach the same performance as the centralized learning method. Also, since our method does not have a lot of restrictions on the base model loss function, this method could be easily applied to other federated learning projects like classification or registration. And the future direction could be applying this method to projects other than segmentation in federated learning, or to implement more complicated recurrent neural networks like long short-term memory model or transformer. That concludes my talk, and I can take questions from now on. Thank you.
Okay, is there any questions? Nobody. Okay, let's continue.